Okay, let's say you have the graph of a curve like this, and you want to rotate that curve around the x-axis. So as you rotate this curve around, you end up with a surface. So it's as though you rotate your curve and you end up with the surface, and you can ask yourself, what's the surface area of that surface compared to the length of that curve that you had. So if you knew everything that you had to know about the curve, then how can you find the surface area of that surface? The idea here behind this formula is that you can think about this as a lot of little cylinders put together. So let's say I take this cylinder right here. So this is obviously not exactly a cylinder because my curve isn't a line, it's curving. But you can imagine that this disk is approximately equal to a cylinder. And to find the area of the cylinder, I need to find, again, maybe cut the cylinder like this, open it up, and it becomes this long, thin rectangle. And so to find the area of this rectangle is, I just need to multiply base times width. And so the base for me will be the entire circumference of the cylinder. So if you imagine all of this here in brown, this is this length here of the cylinder, the base, and back to my curve, this is what I have. This other circle around the surface, and that's 2 pi r, 2 pi radius, but the radius as I go around, the radius is this distance, so it's the distance, that's the value of y, so this is 2 pi y. That's exactly this number that you see right there. And now the height or the width of the cylinder, it will be, so let me choose another color, maybe orange, is this, which is this, which is this. So that's approximately the length of the curve, that little piece of length. So it's the ds. And if you remember the formula for arc length of a curve, this is exactly what ds is. Very, very small piece of the curve has length approximately equal to this. And so this is where the formula comes from. As you multiply these two, you get the area of this rectangle, and then base times width, which is the same as the area of each little disk, or sorry, each little cylinder, that as you add together becomes the integral that you see in front of you. Very simple to apply this formula though. If you don't remember exactly what the idea is, you can always just memorize the formula as needed. I like knowing the idea because if I forget the formula, I get to come up with it very quickly. So I'll go back and solve this example with you. Let's say I have a surface that's rotated, that's obtained by rotating this curve right here, x equals t cubed and y equals t squared, from t equals 0 to t equals 1 around the x-axis. So this is something that I have to pay attention to because that's exactly what happened on my example. So all I have to do is just set up the integral of 2 pi y root x prime squared plus y prime squared dt, and from alpha to beta or a to b. So for us this will be 2 pi, whereas y t squared, the integrals from 0 to 1, and the root is x prime, so 3t squared plus y prime, so 2t, that's dt like so. So I have to solve this integral. don't worry about this 2 pi. This is a constant. I get to write it outside of the integral. Just gotta pay attention that I don't forget about it until the end. And then I got a couple of choices. I have a 3t squared. Let me double check that I've done everything correctly. Oh, this is actually wrong. I feel like I'm getting a little tired. I'm making too many mistakes. I forgot to square them. Right? I took the derivative x prime. That's 3t squared. But still that has to be squared because this is x prime squared. And then I took the derivative of y. Y prime is 2t, but then that still has to be squared. So I still have some hopes that this integral isn't going to be terrible. This is 9t to the power 4 plus 4t squared. That doesn't look so bad. Does not look so bad. I get to factor out a t squared now. And then that becomes 2 pi integral 0 to 1 t squared. And then that's going to be t squared. And then I have 9t squared plus 4. Actually, let me factor out a 4. Let me do that. Because I'm starting to see. Let me do this. Let me factor out t squared. This is the root of 4t squared. So I'm going to factor this out, and then I'll end up with 9 over 4t squared plus 1. I think this is going to look better. And you can see that the factorization is correct. If you multiply this by this, the 4's cancel. And then the t's multiplied to give me this. And then if you multiply this, you go back to what you had before. And now I get to bring this entire thing out to get that this is 2 pi 0 to 1. This is 2t cubed root of 9 over 4t squared plus 1. I think up until now I've escaped trig substitutions, but I see that probably I won't have any escape right now. I think I'm going to have to use a trig sub at this point. Just before I do that, I just like to always go back and double check my math, because sometimes you'll make a mistake. But it seems okay. Spend a couple minutes, maybe a couple seconds looking at it again. Make sure I haven't made any obvious mistakes. But if you find one after the fact, just let me know. I'm okay. I'm okay with the fact that I'm wrong all the time. That's fine. No one's perfect. Okay, that looks fine, I think. So I'll try and make a u sub, see what happens. Sorry, a trig sub, right? As I look at this, I see that this kind of resembles a trig identity that I know, tangent squared theta plus 1 equals the secant squared theta. So this kind of resembles that, because there's the plus 1 there. So I'm going to say that the tangent of theta is the square root of 9 over 4 t squared. So I'll say this is 3/2 of t. This is the tangent of theta. Because then when I substitute that back in, I'll end up with, so I'm not concerned about this 2. I'll bring it out with the 2 pi. There's a t cubed that I'll handle in a second. But this will be the tangent squared of theta plus 1, which will be the secant squared, which goes in here, and then I get to cancel with the square roots. And then right here, I'll have t cubed. So what is t though? If I look at this, isn't t the same as 2/3 tangent theta? So I get to write that out there as 2/3 tangent theta cubed. But then there's the dt that I also have to take care of. dt equals 2/3. The derivative of tangent is secant squared. So that becomes the final form of my integral. Two-thirds secant squared theta d theta. So now I have to solve this. I wonder if this is even better than what I had before, but we'll see. I still haven't handled the limits of integration. I just want to see what that's going to look like. So as we discussed before, this is going to be the secant squared. I'll take the square root of that. It's going to be just the secant, but I already have a secant squared here. So I'm going to handle it as 2. All of this I'm going to write as 2/3 of secant cubed d theta. Now this right here, I'm going to cube the 2, that's 8, cube the 3, 27, and then tangent cubed of theta. All of those numbers, I don't quite care about them. Bring them all out. It's not that I don't care about them, it's that I get to bring them all out of the integral. So this is 4 pi times 16 times 27 times 3. And then now I have this integral, tangent cubed, secant cubed theta d theta. I haven't again handled the limits of integration. I'm going to go ahead and move this further down. I thought I had enough space. All right. This is not bad. This is a little better than it could have been. Now when I multiply the 16 times 4, I'm going to get a 40 plus 24, so 64 pi over 81. And this right here, don't want to worry about the limits of integration for now. I can write as tangent squared theta, secant squared theta, and secant theta, tangent theta, d theta. So this is something that I can do. If I multiply these again, I'll go back to secant cubed. If I multiply these again, I go back to tangent cubed. So it seems like I'm all good right now. And now this is the point where I can make a u sub, right? So I can make a u sub here, because this is the derivative of secant. So if I say that u is secant theta, then du is going to be secant tangent d theta. So this is exactly going to be my du. This is u squared. And if you go back to the original identity that we discussed, that tangent squared plus 1 equaled secant squared, then tangent squared plus 1 is u squared, and tangent squared is u squared minus 1. So then you get to solve this integral. As 1 minus, u squared minus 1 times u squared du. And then again, I haven't looked at limits of integration at all. But this is not a problem. This is u to the power 4 minus u squared. Then I integrate du. So now I have to do a u to the power 5 over 5 minus u cubed over 3. And then I have to plug in the two limits of integration. I'm going to let you do that yourself. Go back, see if you can follow along and trace, find out the correct limits of integration. Look back, right? You had that t was 1 and then 0. What does theta have to be when t equals 1? This is what you have to figure out. You say when t equals 1, tangent theta is 3 over 2. What's theta? And when t equals 0, tangent theta is 0. So what's theta? You go in here, and then when you change it back to u, or if you want, you don't have to do that necessarily. You can go back and think, oh, isn't u the secant of theta? So this would be secant to the power 5 of theta minus secant cubed of theta. Evaluate it at the two limits of integration for theta now. And then you can go back and figure out what's the secant of theta by making a triangle here, because you know this is the tangent of theta. So if the tangent of theta is 3t over 2, you can make a triangle, because this is the opposite over the adjacent. So theta needs to live in a triangle like this. We can use the Pythagorean theorem to find this hypotenuse as 9t squared plus 4, which is precisely what we had before. You see that? Go back. Go back. See, that's exactly what secant squared of theta was. Right here inside. So this root was the secant of theta. Now you can replace that with the secant being. Let me move this down one last time. And as you know, the secant is the cosine, the reciprocal of the cosine. So instead of adjacent over hypotenuse, it's hypotenuse over adjacent. Then you have root 9t squared plus 4 over 2. That will be the secant, but then to the power 5 minus 9t squared plus 4 divided by 2, with then cubed. And then you're evaluated between these two values, and now it's 0 to 1, because we're back to t, so we go back to the original limits of integration from 0 to 1. So I'm not going to plug in the values, I'll let you do that. Just plug in the 1, plug in the 0, you're going to get a root 13 there. Because when you plug in 1, this is going to be the square root of 13. This is going to be 9 plus 4, 13. So I'll let you finish this up. The answer is over here on the top. I think I haven't made any huge mistakes, but you never know. The 64 is here. Maybe it's going to be It's looking fine to me. Who knows? Now, this one I'm not going to solve. I'll just set it up. Note that the difference here is that you have a curve rotated about the y-axis. So now the shape is a little different. And the curve gets rotated like this. So now the radius is no longer y. The radius is x as you go around. So the formula changes to 2 pi x, but then still the same thing. X prime squared plus y prime squared dt, but now you're given the t limits of integration like before, so there's no big worry. You set it up. X is 3t squared. X prime is 6t, that's squared. Y prime is also 6t, that's squared. dt, and that's incorrect, because y is 6t squared. Squared now, because y prime squared, dt. And then you follow similar procedures to the ones before. Setting up is the new stuff that we're talking about now. Solving the integral is something that you've learned in a previous calculus class. So I hope this made sense, and I hope you were able to understand the whole process.